All right, we need to pick up the lectures on sparse models, and hopefully we can do at least half of the Lasso material today as well. There's a lot of modifications in the slides as of this morning, so in case you have downloaded the slides earlier, you will need to download them. Okay, so let me just bypass all of these things. So you remember it's all about variable selection, right? So if we have an input of high dimensionality, the problem we are trying to address in the next few lectures is, do we need all these input variables or all these input futures, if you like? And so we introduce this variable gamma j, a binary variable, that is 1 or 0 if the future is relevant, 0 if it is not relevant. And we wrote in a very compact form the posterior of gamma in this form, where f of gamma is basically minus the log of the normalized posterior. So this is the marginal likelihood, and this is the prior. And one of the things we started discussing on the last lecture is that it is not trivial to actually explore the space implied by this posterior. So if you have, if you have 10 variables, it's basically 10 to the 10th type of models. Exploring all of them will require, in essence, to calculate this function f of gamma and do comparisons. And even worse, whatever method you use, you will never be able to discover the true sparsity in your problem. So one of the examples we were discussing is generating data on a simple Gaussian type regression function. So you can start with a W defined like this with some sparsity. You see a few zeros here. You specify sigma square. And then you give some inputs x, and with some noise, Gaussian noise, you compute y. So if you try to actually use whatever method that explores this posterior to discover back this W, most probably the majority of the methods will fail. Bottom line, this is not a trivial problem, and discovering the data generation mechanism, it's not an easy task. So in this problem, the true models are basically, it's a model that includes variables 2, 3, 6, 8, and 9. And if you somehow compute the marginal likelihood for all the models, and you rank them on posterior probabilities like this, you will see that you know where C, 2, 3, 6, 8, and 9. Maybe, I don't know if it's further down, but somehow you don't see it here. So, so one of the possibilities we discussed was to actually compute the marginal posterior of each of the gamma j variables alone. So that's what you see here, all right? And you can see immediately that variables 2 and 6 and 9 are obviously in the correct model, 2, 6, and 9. But when it comes to 3 and 8, you see 3 and 8 are there next, but also there is 5 and 7, and 5 and 7, they're not in the model. So if you say you're going to put a threshold and anything that is above, let's say here, is included, then yes, you will include the variable 5, and that's the wrong variable that has nothing to do with the data generation. Of course, we may want to say, yes, this is the true model, but is it really this a unique problem? Is there any one selection of W's that actually generates the data? All right, if you think about it, maybe there is some other combination of W's that sort of gives you similar data. Okay, all right. So we discuss briefly sort of the most primitive model, a prior model on gamma to induce sparsity, and that's the spike and slab model. And so effectively what we do is we introduce a prior that's a Bernoulli distribution for each future j. It factorizes over j. So pi 0 is the probability that the future is relevant, and this is the zero norm that effectively accounts for the number of the non-zero variables in the model. Remember, that's the zero norm. It's if you take all the variables that are 1, it's basically the number of non-zero elements, the non-zero futures that are relevant to your problem. So we rewrote this prior in this nice form. I want you to look at it because I'm going to be using sort of this form later on in the slides. Lambda is defined as log of 1 minus pi 0 over pi 0, and that's this norm, the zero norm of gamma. Okay, so the spike and slab model, to go directly to the heart of things, is the equation that you see on the bottom. If the future is not included, is not relevant, basically the probability of W given gamma and given sigma squared becomes a delta function. So you can appreciate that when you calculate the marginal likelihood, if this W gives it's a delta function, means it will be integrated out. So that variable will disappear. It's very important, right? So that variable will disappear completely from the marginal likelihood. If the future is to be included, then you take this to be a Gaussian. So sigma square is the overall noise level. There are various versions of this, and the sigma W is sort of a parameter that allows you to play with. And in principle, if you make it to go to infinity, you get literally a uniform distribution out of the equation on the bottom. Now, there are variations of this, because you have to compare here the delta function model with the Gaussian. This never works nicely, so not only that, by having the delta function, you eliminate all the j futures for which gamma j equal to 0. So what you can do is you can put another broad Gaussian there, so you can actually have a model with two Gaussians. And that's a little bit better than the model that you see on this equation. All right. We're interested if you're going to compare models, or the models require that we compute the marginal likelihood. Right. This is what we started, and the marginal likelihood is basically the denominator, if you like, on Bayes' rule. So this is the likelihood, and this is the prior for W, this is the prior for sigma square. And actually, I missed a slide, which is very good, so we can save time. So remind me, and I ask you the same question, what does the subscript gamma means in this equation? Huh? The active components, you remember, right? Here, we're integrating in W, and the W's for which gamma equal to 0, we have a prior that's a delta function, and that delta function will be integrated out. Will give you 1. So effectively, when we write it like this, we have integrated the irrelevant variables out, and we denote all the other variables with a subscript gamma. There's nothing else. But here what is important is this model, it tells you get rid of these variables, it integrates them out, and only has the variables for which gamma equal to 1. Okay? So everywhere you see gamma is basically, it's the same equations as if everything was in place, right? All the futures were relevant, but here we specify the relevant futures and the number of them using this subscript gamma. So if you can generalize this, and actually instead of using the original spike and slab model, you can use a more general Gaussian here with some covariance metric sigma gamma. And so if you generalize this term here and you plug it in there, and I suppose, okay, this is conditional sigma squared, okay? I was ready to say what happened to the integration of sigma squared. So if you condition sigma squared, so you don't integrate on sigma squared, Gaussian times Gaussian, you can actually use the equations for linear Gaussian models and write this as another Gaussian with this covariance. So sort of you can appreciate the fact, right, that we have an analytic formula under the spike and slab model, where if I give you a model, which means if I tell you what the vector gamma is, what variables are in and what variables are out, you can actually analytically compare, this is the marginal likelihood, and you can do all the calculations analytically. Okay? Of course, if you have 2 to the 10th models, this comparison is not very helpful. So we have to integrate sigma square as well, and we know the prior we put on sigma square is an inverse gamma prior, or you can make it an informative and you make it a Jeffreys prior, which is 1 over sigma square, the way we have seen it, and there is, you can get actually an exact answer for the marginal likelihood with sigma square integrated out. I strongly advise you not to take this blue equation as being Chinese to you, because this type of calculation comes everywhere, all right? It's sort of a, you may think that it's weird equations and symbols, but it's sort of a standard equation. It's very standard, okay? I mean, effectively, we had 2 Gaussian models and an inverse gamma model, or a Jeffreys prior. This is what we did early on in regression. The only difference here is where there is capital X in the design metrics or sigma, I have plugged in an index gamma to indicate that what variables are in the model and which ones are not, okay? So again, if you give me gamma, it's like, you take the design metrics and you eliminate all the columns that correspond to gamma equal to 0, and that will give you the matrix X gamma, and you can do these calculations. All right. Now, if somehow your problem is something different, right, and it is, and this integration cannot be done, we already have seen an approximation to the marginal likelihood, and that information to the marginal likelihood comes from the Bayesian information criterion, where the approximation looks as follows. You calculate, so this is the log likelihood, marginal likelihood. You approximate it with the log likelihood, where for W and sigma, you use either the maximum likelihood estimate or the map estimate. All right, usually people use the MLE estimate, that's way easier. And then there is a penalty term that we already have seen this in earlier lectures. And gamma 0 is effectively the degrees of freedom in the model. And the degrees of freedom in the model means how many variables do I have. And that norm gamma 0 defines, right, how many variables I have on the model gamma. So again, where is this being used? It's used, if this calculation cannot be done, all right, you cannot get even an approximation of this, then the next easiest thing to do will be to use the big criterion to approximate the marginal likelihood. And again, a classical likelihood term plus a penalization complexity term there. So if we put all of this together, if you put this marginal likelihood and the prior for gamma together, you're going to get these 2 terms plus that, okay? So we have, in general, a likelihood term, and then a penalization that says the model should not be very complex, right? This is, how do we call this in Bayesian statistics? It's like fit the likelihood as much as you can, but don't make the model complex. So who says that? What's the rule that says that? Occam's, say the whole sentence because my brain has, Occam's what? Razor. Razor, thank you. Okay, so this is what we have. Okay. All right, so let's continue now with L0 regularization, which actually is not going to be very useful at the end of the day, but before we go to L1 regularization, we have to see the L0 regularization. So the L0 regularization looks like the previous model, but it's a little bit different. So I'm writing down the equations. Again, we're looking for regression, okay? So for every x, right? So this is my regression function, which is a Gaussian, with some noise sigma square. But notice in the mean, instead of having W transpose x or W transpose phi of x if you have some future space. What we have here is we have gamma and w coming together. All right? So gamma and w come together, and which means at the end of the day, when we're going to try to do estimation, we're not going to be able to estimate w alone, but the only thing we can identify is the product of gamma and w. Okay? So I'm going to show you why is this different from this previous model momentarily, but this is how the mean looks like, and the gamma is exactly as before, a Bernoulli distribution, and the weights, we take them to be a Gaussian, and you can take the same form as before. Here I have a simple Gaussian with the same variance basically for all the WJs. So here is the major difference from the spike and slab model. You remember in the spike and slab model, if I know gamma j, it tells me which WJs are 0 or 1. And then the WJ defines what gamma is. In this model, to define y, I need to know what gamma j is, and I need to know what wj is. So the dependencies are completely different between the two models, and you will see shortly they lead to different formulations. Okay, but when it comes to identifying w, you cannot do it alone. You have to identify gamma times w. So if you write the prior of gamma and w, for w you have a Gaussian, and for the gammas you have a Bernoulli distribution exactly as before. So if you form the negative log posterior, anormalized, so it's log likelihood plus log prior, and I multiply by minus 2 sigma squared, so this looks a little bit better. What you get is, from the likelihood, you get y minus x, and you notice here you get the product of gamma and w's, all right? This comes from there, okay? So this means you have two vectors and you multiply each component together, okay? So this is the product of gammas and w's. So here is one penalization term of w squared. So this is an L2 sort of penalization, the way we have seen it before. And this is L0 regularization for gamma. And lambda is exactly the same as before. We just have multiplied by this factor minus 2 sigma squared. Okay. So what you can do is, often you can take this sigma w to go to infinity. And if you take sigma w to go to infinity, this term here gives you 0, which means that effectively, if I get rid of this term, right, what do I do differently from this spike and slab model? If somehow you get rid of this term completely, what does that mean? I mean, this term effectively, right, pushes the magnitudes of w's to become very small, all right? So you say, you know what, do not regularize this. The only regularization is going to come from the gamma vector, okay? So you don't, you don't define, so you don't basically regularize anything coming out of the likelihood, okay? So effectively, this joint log likelihood looks like this, okay? And so explain to me the notation here so I can see this term. So what does now x gamma times w gamma means? Remember, right, that I need my gamma vector, and at the same time I have a w vector because they multiply each other together. What do you think w gamma is? It says here, basically, w gamma is the w that is indexed by gamma equal to 1, okay? And obviously, if I have a product here of gammas and w's, only the components of w will appear that have gamma equal to 1, exactly as we did with the spike and slab model. Okay? So this thing that you see here is L0 regularization. All right? And it's sort of not an easy problem to handle, because you notice this is a discrete variable, right? And this is a continuous variable. So the way it looks like, it's not very appealing for doing optimization. So what people do is they approximate this with what the equation that you see on the bottom. And can you guess, just looking at the two equations, what's the miracle that you can think you're doing here, going from this equation to that? So obviously this is a discrete variable, this is a continuous variable. So what exactly do we do? Remember, if gamma equal to 0, the product of gamma and w, that component, would be equal to 0. All right? So effectively, when I sum here how many gammas are non-zero, isn't it that the same as summing how many w's are non-zero? Right? Because at the end of the day, the two things, the product is that it's coming together. The only difference is when you look at this versus that, here, the only unknown is w, and it's a continuous variable. All right? Here, w gamma is a continuous variable, and gamma is a discrete variable. So, so this is what literally people call L0 regularization. And again, the techniques for solving this problem are not easy, because the you can think, you know, when you say these are the non-zero w's, if you keep one component of w in or out, this becomes a non-smooth optimization problem. Basically, you start jumping from one value to another, so trying to optimize this would not be an easy thing to do. All right. So let me discuss very briefly, if you have any of these models, right, and you want to figure out which variable should be in the model to explain the data, how do you do this, okay? So all the algorithms, at the end of the day, they use some form of heuristics, because if you have d futures, means you have 2 to the d models, and there's no way you can actually enumerate all of these models one after the other and try to make sense out of it. So you have to do some magic. And the idea here is you're going to start with some model that has some of the variables in the model, and then you're going to start making some moves and say, what variable should I add? And you will try to add one variable at a time. Or you will try to remove one variable at a time. So if I have, let's say, variable 1 and 3 and 5 in the model, now you're going to say, which variable that is added to the model will actually increase the marginal likelihood. Okay? So obviously, you're going to have to solve this problem for a number of scenarios where you flip, if you like, one of the gammas from 0 to 1, or maybe you flip one of the gammas that's equal to 1 to gamma equal to 0, but somehow the heuristics will come if moving from gamma to gamma prime, it's an easy computation. An easy computation means if maybe the design matrix x gamma to x gamma prime can be updated with very low computation. So if you can do this, sort of heuristic approaches will work well on this type of things. So effectively, you remember in the marginal likelihood, you had to calculate this x transpose x for all the variables where you keep only the variables that have gamma equal to 1. So if you can go from this to that without having to recompute things, then maybe these heuristics will work out well. So let me give you some ideas, right, on what you can do. I think the slides, basically, we have lots of details for you, and I think they're not very difficult to read. So think that you start, let's say that we have 4 variables, and you start with 0 variables. Now, it's easy to say, look, if I'm going to flip one of the variables on, I can either have variable 1, 2, 3, and 4. So you're going to have to run 4 problems, all right, by incorporating only variable 1 or the variable 2 or 3 or 4, and you're going to compare which one maximizes the likelihood, okay? And then you will say, oh, you know what, it's model, let's say, 2. If it is model 2, the next step, I am adding only variables now, right? So, but if it's model 2, then you're going to say, what can I add to model 2? And obviously, you know, for model 2, you can add the variable 1 or the variable 3 or the variable 4. And so you try those. And that way, as you keep adding more variables, these are all the possible options you will have. You can find sort of what is the combination of the gammas that gives you this optimal improvement, if you like, in the context of the marginal likelihood. Obviously, this calculation, it doesn't mean necessarily it is cheap, but it's something for a few variables, you can try it. Here is something more sophisticated, and the only reason I'm going to do these techniques is because we will see similar settings in the context of the Lasso algorithm. So let's say that you have you have a current model at, let's say, time t that includes variables gamma t. Okay? So now I am only going to add a new variable. All right? So actually in this model, I don't believe you remove variables. Okay, so in this model, the complexity lambda equal to 0. So we're only adding variables. Okay? So I want to add the variable j that is not on the set gamma t. All right? And I'm saying, find for me the j that minimizes the error. All right? This comes from maximizing the likelihood. All right? This is the mean square error, or you know, that's what we have, right? Where on the set gamma t I have added variable j, and once you find me j, then minimize me and tell me what w is. Does the equation make sense? We have a model. We have decided what variables are in at the current time, and that the index is gamma t. So now we're going to add one column to the vector to this design matrix X that involves also variable j that is not in the active set. So we're going to find the error that we do. That's this L2 error here. That's from the likelihood, right? From the exponent of the Gaussian. And we're going to say, find me the j, not in the current active set, that minimizes this error. And then once you find me that, compute what w is by solving a least squares problem. Okay? It's as simple as that. So obviously, when you do this, you're going to have to, you know, if you have, let's say, at present you have d subscript t variables defined by gamma t, all right? You're going to have to solve a total number of least square problems that is d minus dt. So that's, you know, it's an expensive calculation. It's not a trivial calculation. So this algorithm goes with the name orthogonal least squares, or greedy forward selection. And it's forwards because we only add variables. We don't remove variables, right? And this is what makes this computation easier. So lots of methods try to even do more greedy type of approximations than this equation that you see here. And here is one approximation. I don't want you to read anything. Only look at this equation. So pretend that the rest of the text is not there. So look at that equation. Tell me what is more greedy now that we do to get this approximation. The notation is the same. And as I see there, I should have put x subscript gamma t, right, the way we had here. X subscript gamma t, I forgot that. All right? So, but what do we do here? What is different? And again, don't read. What does it say there? WT, which means what? Remember in the previous problem, we will do the minimization and find the W that solves the new least squares problems in the bigger space. Here, what does it say? Keep the w's that you computed before at time t fixed, and find the coefficient when you add column j. Right? You have your vector, you have the design matrix X, you add a new variable, all right? And you say, look, the w's that correspond to time t, I'm going to keep them fixed, and I'm only going to add a column j, and I'm going to ask which column j should I add so that this error is minimized, all right? And once I compute this, find me what the coefficient beta is, because wt is constant. It's what I calculated before. And we follow? Who are sleeping? Okay? All right, so if you do the optimization with respect to beta, it's obviously a least squares problem, but for a scalar variable, and you see beta is basically here. When you look at the calculation, is the column j of x times the residual that you have currently. So it's the column xj times how much error do you do at present, right? That's the residual, okay? So effectively, you don't have to do, if you assume that the columns of the design matrix are orthonormal, so that this norm is equal to 1, effectively it's like saying, look, let me look at all the columns of that they are not in the model, or variables that they are not in the model. Let me find this product of xj with the current residual, and let me find the future j that maximizes that. It's like a little pre-processing, multiplications of the residual with the columns that are not in the model. So effectively, you're looking for the column that has the maximum correlation with the current residual, okay? And obviously, this method is not going to be as accurate as the previous method because we don't update w's, all right? We only update this beta here to make a decision what model to include. But in principle, what you can do is once you compute beta and you say, oh, I'm going to include this j star column in the model, then you can go and solve one least squares problem and update the w for that new least squares problem, and that will give you a new wt, and then you continue, etc., etc. Okay? So this method goes with the name orthogonal matching pursues, and also you will see it in the literature on Wikipedia has a whole site on this as least squares boosting. Okay, so that's a standard type of technique. You can do infinite techniques, right? And you can start imagining what is possible. So I'm just, without even remembering the details here, it says backward selection. So I can imagine maybe a backward selection is something that you start with all the futures in, and you start removing one future at a time, right? And in some sense, that makes sense because you will be able to actually model the effect of each variable in the presence of all the other variables. It's like a mean field approximation. Because before you're saying, should I add this variable or not, when all the other variables were not there. So how can you decide if a variable is important when you have not seen the effect of the other variables? Okay? So this obviously will be way more accurate, but if you have a large-scale problem trying to do these calculations and start with all the variables in the model and then removing them, that would be computationally sort of prohibiting. Okay, and if you want to be Bayesian, actually, and if you want to be fully probabilistic, you can actually explore the posteriors, P of gamma given D, okay? And I know those who took the class in the fall or last year, you already did this in the homework, but it was, you forgot about it. So you did, but you did not. But the idea is, you can use Metropolis Hastings to explore this with moves from gamma to gamma prime that are similar to what we discussed. Do I add a variable? It's birth-death type of moves, okay? And for each of them, you have to design an acceptance probability and explore this, hoping that at the end you will converge to something reasonable. You can actually, there's a lot of things in the literature. You can do expectation maximization. And from what I gathered, these techniques don't really work, but also you can do variational methods that unfortunately we're not going to have a lot of time to discuss in this course, so you can use variation approximations to do this type of problems. All right, now we're in business. It's 1:05, so let's see how much we can do with Lasso. Not a trivial topic to teach, and I was looking at the slides only last night, and I said there is no way anybody's going to follow. So I had spent my nice evening and nice morning in putting slides, and as you look at them, you say this is wrong, because I'm sure there must be lots of typos as I was writing. So let's see what we have. All right. So we discussed about priors, right? We had priors on gamma and leading to L0 regularization. So let's introduce for W a prior that looks like a Laplace prior, all right? And in case you forgot the Laplace prior, you don't need to know anything else, but it has this form. Obviously, it factorizes here. We take it to be the same over all the futures. Is minus lambda times the absolute value of Wj, okay? And actually, everywhere in these lectures, we don't really put any penalty, if you like, on the bias term when we do regression problems. So the priors on W0 is 1, or the bias term has been integrated out, so we don't have to bother at all about it. So remember, there's no bias term in these calculations. So we put a prior on W that looks like a Laplace prior, all right? So if that's the case, then let's see how the negative log likelihood, the negative anormalized posterior, if you like, looks like. So this is the likelihood, minus log likelihood, and this is minus log prior, all right? So this is the negative log likelihood term. And then from here, you can immediately see that the penalty term that controls complexity is the L1 norm of W. And the L1 norm of W, in case you have not seen it before, it is the summation of the absolute values of the W's. Remember, before, when I had the W0 norm, it was the sum, the numbers of the W's that they are non-zero. Here, W1 is the sum of the W's. Okay? So the sum of the absolute values of the W's, that's the W1 norm. Okay? So for example, if this thing is the negative, if the likelihood is a Gaussian model with some bias term and W transpose xi for the regression function, basically this is how it looks like, all right? So what you see here, minimizing this, is performing a map estimation. Really, we are maximizing the anormalized posterior, but what is new here is that we do this with a penalty that is an L1 regularization penalty, something we have not seen in this course yet. So we need to know what exactly this means and why it uses sparsity and the likes. All right, so first let me give you, some graphical representation why there is sparsity in this model. And to do this, I'm going to state the following, that is, it's applicable actually even if the norm here was any other set of norm. But this is the theorem. If you want to minimize this, all right, with some regularization parameter lambda, this is the same as minimizing, this is, what is RSS? Residual sum of squares, okay? It's the same thing we had before, right? Is minus the log likelihood. So this is the residual sum of squares, okay? So this optimization problem is the same as minimizing the residual sum of squares without a regularization term, but with a constraint that this norm of W, the L1 norm, is less or equal to some value B that depends on lambda. Okay? And this is a universal theorem, basically, in constraint optimization. So you may want to look carefully in every direction. I think I know we have used it, maybe not in this course, maybe in last fall in other settings. But the idea here is this problem, it's equivalent to this, where now, so it's like you bound this norm by some value B, but this B is a function of lambda. So if you want W to be less or equal to some very small value, this is a very high penalty, and high regularization. If you take B equal to infinity, it's like regularizing nothing. And the algorithm that does the solution of this problem is called Lasso, and Lasso stands for least absolute shrinkage and selection operator. Lots of buzzwords there. Least absolute shrinkage and selection operator. Okay? If you Google it, you will see there must be more than several $1 million of citations that are coming under the Lasso algorithm. Okay? So obviously must be important and must introduce important ideas. So where is the sparsity coming in a visual sense? Okay? So what I have here is, I have the contours of the likelihood, which you remember it was Gaussian, so there are these ellipses. So this W hat is the MLE estimate of W. And you remember our problem says minimize basically this, all right? And at the same time, satisfy. So here I'm basically repeating the two problems. If the norm was L2, right? I'm showing you the same equations. Maybe I should split the slides. But I effectively wanted to do is, I wanted to do a comparison of this problem, which is of interest to us, all right, with the same problem if this norm was an L2 norm, okay, which is that. So this is the setup of the classical problem we have seen, okay? And this is the setup of the problem where we're minimizing the L1 norm, okay, that looks like this. So visually, can you see why this setting here leads to sparsity and this does not, especially in high dimensions? I mean, the idea here is, right, you keep growing your ellipses until you hit a constrained surface to find a solution, because this needs to be satisfied there, or this needs to be satisfied, which is there. And the question is why this, the L1 regularization leads to sparsity and the L2 regularization does not. Can you see visually? So when you grow this ellipsis until you hit the constraint, what do you hit first here under L1 regularization? You hit one of the coordinates. All right? Here there is multiple points because of the symmetry that you have that you can hit. So if you hit this coordinate, you can see one of the W's is equal to 0, all right, and that's how the sparsity comes. And obviously, if this is high-dimensional problem, you can imagine the amount of sparsity you will get would be significantly higher than in the plot that you see in 2 dimensions. Now, you may say, I don't believe these things, you know, even though I have a lot of pictures from an earlier lecture last fall to explain this. But if you really don't believe this, the only thing someone can convince you is if you see what are the constraints implied by this optimization problem versus the constraints implied by that we have seen before with regularized least squares. All right. So obviously what is unique about Lasso, right, without doing any calculations, we have these corners of the L1 ball where we need to satisfy those constraints. And so this L1 ball is non-differentiable as sharp corners. There is no rotational invariance the way we had it with the L2 regularization, and which means all of these ideas of doing singular value decompositions that explore symmetries are not applicable here. And obviously, as we will see, the algebra is way more difficult when we do Lasso. Things are not trivial. All right, and if you want to appreciate, before I start doing the algebra, also why L1 regularization gives sparsity versus L2 regularization, take a vector W10, right, and compare it with a vector W 1 over square root of 2, 1 over square root of 2, all right? Both have the same magnitude, okay? Obviously, this is sparse. One of the features is out. If you take the L2 norm, you can see those things, they say they are the same, no difference. But if you take the L1 norm, you can see that this vector has less L1 norm than this vector, okay? Remember that the L1 norm is the sum of the absolute values, so it's 1 here, and here is 1 over square root of 2 plus 1 over square root of 2, it's square root of 2. So, so the penalty, so this is desirable, right? This will be selected by the Lasso algorithm, and it is desirable versus this, but in L2, it doesn't make any difference. A commentary before you see the algebra is the following. When we did least squares, right, with L2 regularization, remember all solutions were analytical. You can write, if you have a given regularization lambda, you can write the solution, x transpose x plus lambda I inverse times x transpose y, your classical least squares problem. You can write it analytically, okay? If the model is a generalized linear model, you remember we did not have analytical solutions, but we had iterative methods that when they converge, they give you the right answer. And if you recall, this method that we discussed was the IRLS, which stands for what? Iterative reweighted least squares method, okay? So if you have a generalized linear model, you don't have an analytic solution, but there is an iterative algorithm that actually converges to the right answer. Here, with Lasso, we will see the solution is basically a direct numerical solution, okay? Which means that if you have a good computer, basically, you can get the exact solution, but there are no iterations the way we have in generalized linear models. So basically, we're not going to iterate anything. We're going to say, this is the solution. We can compute it. So somewhere in between, if you like, the ordinary least squares and the iterative reweighted least squares, that's where Lasso is going to belong. Okay. A little bit of mathematics now. Okay. So we, obviously this regularization term is non-differentiable, and the only thing we know how to compute, to do optimization is to take derivatives, set them to 0, right? That's how we got least squares. So this thing is not differentiable, so this is not going to help us. So we need to define here a new set of derivatives. We need to define something different from the classical derivative that you know, and that definition is what is called a subderivative or subgradient. So if you have a convex function from some domain J to the real line, so the subderivative at a point theta 0 is a scalar g, or if you like, any scalar g, that this inequality is satisfied. So look at it carefully, right? When you define derivatives, how do you define derivatives? Take f of theta minus f of theta 0 divided by theta minus theta 0, then you take the limit as theta goes to 0. That, if it is unique, that's the derivative. Here we know from this corner that defines this L1 ball, it's not differentiable. So we need to define what's called a subderivative g, which is defined at every point theta 0 such that f of theta minus f of theta 0 greater or equal to g times theta minus theta 0. So you can see, for example, in this point, right, there, if you look on the left, there is this is differentiable on the left, but if you look on the right of that point, that's also differentiable, but what is the derivative? Well, the derivative is basically if you think of any line that has slope between the two lines that you get when you differentiate the left part and the right part. That's what it is. All right, so any of these slopes here that you see, it's a subderivative. Okay, and in principle, we would be interested on the interval that goes from the slope, if you like, to the left and the slope to the right, because these subderivatives will be in that interval between the two derivatives. All right. So that's exactly basically what I said here. If you take a derivative from the left and derivative of the right, basically this interval A to B will define the subdifferential, if you like, of the function at that point. So let me give you one example. Let's take that the function f of theta is the absolute value of theta. This is what we will need for L1 regularization. So this is the definition of the subderivative. If theta is less than 0, right, this is differentiable. The derivative is minus 1, right? This is minus theta, so the derivative is minus 1. If theta is positive, this is theta, so the derivative is plus 1. And if theta is equal to 0, right, you cannot define it, so the derivative is anywhere between minus 1 and 1. So when we define the subderivative for theta equal to 0 is the interval minus 1 to 1. Okay? Now, you will see this bracket with all three options everywhere, because effectively we're going to have to take derivatives of functions that look like this. Okay? We're going to have to take derivatives of that. The notation, by the way, you can use anything you want to, but this is the notation used in books. A subderivative of the function f, function of theta, compute at theta 0. So this is what we use. And obviously, if this derivative, if there is a unique derivative, the subderivative is the same as the unique derivative that you have learned in calculus. Here is what I want you to know, right? And you have to trust that this is correct. You can search it, you can read it in books. So suppose we have a function f, and particularly here we're interested in a convex function f, and we're asking if a point x0 is the global minimum of a function f, all right? So here is the general thing when there is no differentiability assumptions made on the function f. So the point x of 0 is a global minimum of f if and only if the subderivative contains 0, which means 0 belongs to that interval that defines the subderivative. Usually, how do you say if the point x0 is a minimum? You say if the derivative is 0 at that point, then I have a minimum or maximum. Okay? I work with convex functions. But there's not a single value of the subderivative. It's an interval in general. So we say the point x is a global minimum of f if the 0 belongs to the subdifferential. You understand this? All right? So basically, if one of the subderivatives that I get, right, gives me this condition, then the point x0 is a global minimum. So effectively, when we try to minimize these convex functions that they're non-differentiable, the whole trick, the whole story of the Lasso algorithm is to figure out if the 0 belongs to the subdifferential of this objective function that we're trying to minimize. Okay? So we don't set anything to 0. We're trying to compute if the 0 belongs to the subdifferential. All right. So let's start doing some algebra. Okay? I think if you understand this algebra, even if I don't cover the rest of the slides, you should be able to actually follow easily the details. So, so let's, what is our function, right? Minimize the residual, the RSS, the residual sum of squares, which is y minus xw, that's a 2 error, right? And then I have a minimization of the L1 norm, and the only thing I have done, instead of lambda here, I put 2 lambda, so the lambda cancels out, the 2 factor cancels out from the end result. I think in some of the slides I have kept the 2, so hopefully you can understand from the context of the slides if the 2 is kept or not, but here I just put a 2 lambda, okay, so we can get rid of the 2 in the algebra. Okay, so we want to find W, all right, that minimizes this. Okay, so we expand here. And I have done one assumption here to make the algebra simple and to eliminate sort of, so we can concentrate on understanding this differentiation here with subderivatives. So my assumption is that, is it written somewhere? That x transpose x here is an identity matrix. Okay? It has nothing to do with the optimization problem, right? So here I was going to get W transpose X W, and now instead I get a W transpose W, just to make the algebra easy, okay? So you can, obviously you can manipulate the design metrics that this is satisfied, but I'm doing it here so the algebra looks simple, okay? And later on, actually, I keep this term. So expand this with this assumption, we get that. So we want to find the W, all right, that minimizes this objective function. So what is the criterion that we know based on the theorem that I just told you? Obviously we need to find if the 0 belongs to the subdifferential of this objective function. So let's concentrate on taking derivatives with respect to, let's try to calculate one of the W's, in particular Wj. Okay, let's try to calculate Wj. I want you to agree first with me that the derivative of the objective function with respect, let me see, is this correct? Okay, so it says here, the subdifferential of, I'm sorry, here it only looks at the L1 term, okay? All right, so I'm going to come back to this. I was wondering if I miss all the terms. So would you agree with me that when you take derivatives of this term with respect to Wj, that this is what you get? Before I gave you how the subderivatives look for the absolute value, here is not any different, right? Would you agree with me that the derivative of this with respect to Wj, so if the Wj is, remember, this is the sum of the absolute values of the Wj's. So if the Wj is negative, then the derivative is minus 2 lambda. If it's positive, it's 2 lambda. Otherwise, if this is 0, it's anything from minus 2 lambda to 2 lambda. Right? I'm only looking on the subderivative of this regularization term. Okay? So now I am going to have to include the subderivatives of these terms. But for this term, the subderivatives are the same as what? As regular derivatives, right? Because this whole term is differentiable. So here is the answer. If you want to calculate the subderivatives with respect to the jth component Wj, this is how they look like, all right? So you notice here what I added is 2 times Wj minus 2xj transpose y. From where did this come from? Take derivatives here with respect to Wj, you get 2 times Wj. Take derivatives here, what do you get? The xj column multiplied with the y vector, okay, times 2. And what happened here to the w term? There's no w term. Well, it disappeared because this is for w equal to 0. So effectively, the subderivatives of the objective function that we want to minimize the subderivatives with respect to Wj look this interesting equation, okay? So lambda, remember, is fixed, right? We calculate what lambda is going to be. I mean, we set it at the beginning, so lambda is fixed. And we take the derivatives with respect to Wj, and this is what we get. And we have three scenarios. If Wj is positive, equal to 0, and Wj equal smaller than 0. Okay, so the theorem says that to be able to find if something is global minimum or not, we have to find if the 0 belongs to these subderivatives. All right, we have to find if these three terms that we see there contain a 0. All right, contain a 0. So this calculation, I wrote it very explicitly, and if you see any typos, please send them to me. So let me, I'm going to work one of the cases, and you can, the other two are in the notes as well, okay? So let's assume that Wj is greater than 0, okay? So if Wj greater than 0, the subderivative is given by 2 times Wj minus 2xj transpose y plus 2 lambda. And if I simplify, Wj xj transpose y minus lambda. Okay? So basically what I have done is I set it this equal to 0 to see if this contains the 0. All right? I wanted to see if this contains the 0. So Wj equal xj transpose y minus lambda. So immediately we can see Wj is a linear function of lambda. This will have implications later on. Slope minus 1 has an intercept xj transpose y. And because I assume Wj greater than 0, obviously for this to hold, xj transpose y has to be greater than lambda. So, and because lambda is regularization parameter greater than 0, lambda has to be greater than 0 and less than xj transpose y. Okay? So, what's the conclusion here looking at this slide? Just tell me what is, this contains everything we need to know. So effectively, right, we calculated the Wj, and we're asking now, we calculated this by putting this equal, that this is a single value, that this is 0, all right, that the 0 is contained here, that this is 0 the way you set the first derivative equal to 0, and we said, look, this looks like a nice answer for the coefficient Wj, but to be true, we better have this constraint be satisfied. Bottom line, if lambda is greater than 0 and it's less than xj transpose y, then Wj equal to that answer, and that's the final answer. We basically have calculated the coefficient Wj, all right? This calculation will actually be the correct minimum if lambda is greater than 0 and less than xj transpose y. Okay? Remember, right, the subderivative contains 3 terms, so we need to see if 0 can be contained on this term, if 0 can be contained on that term, and if 0 can be contained on that term. So we're doing one thing at a time. So I'm starting, this is a single value. Can it be 0? And the answer is yes. This looks nice, but lambda has to be less than xj transpose y, okay? Let's do so if Wj is negative, okay, which is the case like that, if you set this equal to 0, it comes out that this is also a solution, but for this solution to be valid, lambda has to be less than minus xj transpose y, right? Because you can see here, lambda is we set the Wj less than 0, so this has to be less than 0. So xj transpose y has to be less than minus lambda. Okay? So the two cases, the one for Wj greater than 0 and for Wj less than 0, we can actually summarize the optimal solution with one equation and write it as Wj xj transpose y, like this term, right? Minus the sign of xj transpose y times lambda. So in this case, you notice for this equation to be true, right? Because lambda is positive, xj transpose y needs to be what? Has to be negative. All right, so if this is negative, what do we get here? Xj transpose y is plus lambda. If the sign of this is positive, then we get xj transpose y minus lambda, which is that. So effectively, by looking on the case Wj greater than 0 and Wj less than 0, we have computed analytically the solutions, all right? The global optimal solution, basically. But this solution comes from the first two branches for W greater than 0 and W less than 0, and they are summarized with this nice formula. An extremely nice calculation, and actually, don't know if we're going to have time to discuss it today. You appreciate that this formula gives you the Wj, the optimal, for any regularization parameter. So actually, we may be able, at the end of the day, to compute the solutions for the whole regularization path, from lambda equal to infinity to lambda equal to 0 all at once, with one formula, okay? So the only thing we have not done is the case of Wj equal to 0, right? Because you remember, the whole idea is to discuss about sparsity. There is no sparsity here. There is a Wj, right? These are non-zero. It's either positive or negative. The question is, can we actually get some of the Wj's equal to 0, right? Can that happen? So what do we need to check if Wj equal to 0 is a solution? What do we need to check? Based on this theorem that we discussed about the global minimum of this convex function. So if we want to check if Wj equal to 0, what do I need to check? If 0 belongs on this interval. All right? So if 0 belongs to this interval, right? So it means 0 will be greater than minus 2 lambda minus 2 times xj transpose y, and also means 0 will be less than 2 lambda minus 2 xj transpose y. So let me write down these equations. This is what I just said. If 0 belongs to that interval, actually this is wrong, okay? Remind me to delete it there, okay? So if 0 belongs to this interval, this has to be true, right? And this has to be true, okay? And if you summarize these two equations together, lambda has to be greater than the absolute value of xj transpose y. We're done. Here is the solution for computing the optimal Wj. If the regularization parameter lambda is greater than the absolute value of xj transpose y, the optimal solution is 0, sparsity. If lambda is less than or equal to xj transpose y, the optimal solution is what you see there. That's Lasso. Okay? I mean, that's Lasso, without the theory, with a little bit of heuristics, but basically this contains the whole truth, right? And the only thing we have done to simplify the calculation is we took that x transpose x to be I, so these formulas look basically, we simplify the some of the algebra, but otherwise the Lasso calculations remain intact. Okay. All right. So so what I'm going to do is so remember these formulas, right? If lambda is greater than xj transpose y, this is 0. If lambda less or equal to xj transpose y, this is this value that you see here. So let me just plot W1 as a function of lambda now. So suddenly we can compute the optimal W1 for all lambdas, for all regularization parameters, right? We don't have to invert any matrices or anything like that for all lambdas. And Can you imagine what this value is that somehow it says that for anything greater than that, we get 0? Look again at the formula here. What do you think this value is that makes the Wj equal to 0? What is, look again at this formula, and tell me what is this value there for lambda? Absolute value of x1 transpose y. Okay? So, and here is a wonderful picture that summarizes the solution for a problem. Let me see what the problem is. We generate some data with some polynomials for the 5, all right? So we have 5 W's, all right? And obviously we need to give some training data, we take some Gaussian noise, and we start with a W that has this sparsity. So this is the data generation mechanism, right? I select this W that has 3 of the components equal to 0. I don't tell you that, but somehow we need to know if we can figure out what generated this data, what the W was. Now, what I'm going to do is I'm going to plot the solutions to this problem for all possible values of lambda, right? For all regularization parameters, but the actual data was generated actually from a W that has this sparsity, all right? But we are going to compute a solution for all possible now regularization parameters. So look at this picture and try to tell me what exactly is plotted. How do you understand this picture? So let's start with lambda equal to 0. So what do you see there? I have 5 coefficients, right? So what do you see at lambda equal to 0? No sparsity. What do I solve? A regular least squares problem, because I minimize the residual sum of squares. That's all. Okay? All right. Now, I hit, all right? I hit this value there. Can you tell me what that value is? What is it? Absolute value of what? So obviously, if if you calculate, right, x1 transpose y, x2 transpose y, one will be bigger than the other, so you can actually rank them. Which one is bigger? Okay, right? So you can rank them and say, so in this case, all right, this will be what? What value will this be? This particular value of lambda, what will it be? Absolute value, I heard it. You notice here this W4, right? After that point becomes 0. So according to our formula, when is that 0? X4 transpose Y. All right? So from that point of lambda to this point of lambda, okay, everything varies linearly. Why it varies linearly? Because you remember, what did we say? That the variation of the W's with lambda is linear, with slope either -1 or +1. Right? Slope -1 or +1. So until we hit this point, and what is that point? Absolute value of x transpose y. Okay? And then W2 becomes 0, etc. Okay? So effectively, what you can achieve with Lasso is you can learn the whole regularization path, right, with the same algorithm, as if with the same cost, effectively, of using one lambda. You cannot do this with least squares, because you remember in least squares, like in Lasso regression, you have to invert that matrix x transpose x plus lambda I inverse, right? So you cannot do this. But with Lasso, actually, you get the whole regularization at once. Now, if by surprise you look at lambda equal to 0.5, the only non-zero futures that you have is 1 and 3, all right? So there is solution where the only futures present are 1 and 3. But you notice, right, you can move this line basically from here to there and still have futures 1 and 3. So it's not like you will be able to precisely recover the precise W's that generated the data, but at least the sparsity that generated the data is recognized by this model by having the lambda value vary from anywhere from here to there. Okay, so we have a lecture tomorrow or not? Are you tired as I am? What is the feeling? It's your call. Let's have a lecture because I think, okay, I was ready to say no lecture tomorrow. So let's have a lecture because next Friday there will be no lecture. Okay, so I'll see you tomorrow.